Today I want to give you a panorama of the way that numerical methods have been built into Mathematica. I'll try to give you simple examples that motivate some of the choices that are made and how you can use Mathematica itself to get some idea about the choices of methods that are made. Okay, I've tried to simplify the examples as much as possible for people who aren't experts in any particular field. I'm going to use several features, in particular these monitor functions. So these are available to get some kind of introspection into the system. Here's a simple example using find minimum. I'm going to use evaluation monitor, and I'm going to use it to count the number of times that the function is evaluated, the number of times that the gradient is evaluated, and the number of times that the Hessian is evaluated. So that's what you see. And the number of times the step monitor will count the number of steps that are taken. And that's what you see here at the end of the result. So we have the minimum that was found, the solution that was found, and then this additional information that's been collected. So the second thing I'm going to do is, often when I define a function, I'm going to define a function like this, a standard pattern in Mathematica. And then I'm going to define a second function, which is essentially a black box wrapper. Okay? And what that does is it only evaluates when numbers are given to the function. Okay? And that, in a sense, is hiding the function from Mathematica, disallowing Mathematica from doing any processing on the function. All it sees is this function fn, and it can't get inside and see the actual structure of the equations. Okay? So that's going to give you an idea about the kind of processing that Mathematica can do. If I give it this function, it can go and analyze this function. If I give it this function, then it's prevented from analyzing that function. So the first example is if I use this black box function and I try to find the minimum of this function, then I get a bunch of messages from find a minimum saying it's unable to symbolically compute the derivative. Okay? And when it's unable to symbolically compute the derivative, what it will do is it will use differences of the function itself to approximate these higher order derivatives. Okay? And so it's kind of a numerical derivative that it's using. And this tells you the number of steps that are taken, and these are the number of functions and derivatives. And if I instead take the symbolic form of the function, excuse me, then what you can see is it's able to get the symbolic derivatives of these of the objective function, and it's able to do a much more efficient job of computing, in this case, what's the same local minima. It's found the same local minima, but it's taken one more step, but actually the number of functions evaluations is much smaller, and it's actually got a very slightly more accurate answer here. You can see the last digit there is 1 digit different. Okay, so this was actually much faster to compute this second solution. So here's another example where I'm preventing Mathematica in its optimization routine from going inside the function symbolically. And this particular function is a sum of squares. That's my pointer stopped working. Okay. Is a sum of squares here. And when you have a function that's a sum of squares, a good method to use is the Levenberg-Marquardt method. Okay. But if I give it this black box function, then it can't see that the function is actually a sum of squares, and it will use the quasi-Newton method. And it will use the quasi-Newton method with numerical derivatives. We'll give a message about that. And that's just to show you that the solution is the same, the automatic solution is the same as the solution found, explicitly giving the method quasi-Newton. Then if I use the Levenberg-Marquardt method, then what you see is, compare the two, it's actually found a different local minimum. Okay, from the quasi-Newton method. And it's actually found it much more efficiently, because it was able to do this analysis of the objective function. Just to show you why, let's just take a look at the objective function. And what you see is, if you look at this objective function, there are a whole bunch of local minima. And depending on where you start in this function and which method you use and which line search, etc., it uses, you'll fall inside and locally find the solution of these different minima. So another example is numerical integration. In numerical integration, we take a definite integral of this form here, and we approximate it with a quadrature. So we take a weighted sum of the function at some sample points. Okay? And I'll show you an example of how an integrate will also do some analysis of this particular function in order to choose these particular weights and how they're distributed and where to sample the function. So the first example is an integrate will transform a problem. Let's say I've got an infinite integral here, so the limit itself is infinity. Numerically, of course, you can't evaluate infinity. So what does Mathematica do? It will do a transformation of variables to map infinity to 0. And it does that by taking a derivative of the coordinate and adding the determinant of the Jacobian of that transformation of that variable. Okay, so let's see an example of that in the next slide. Here I have a function. I want to evaluate this n-integrate function many, many times and plot how the value of that integral changes with a value of a parameter in the integration limit. If I actually do this coordinate transformation manually, this is a step that n-integrate is going to do, but I've done it once and for all and evaluated it, something that n-integrate is going to be doing in this plot many, many, many times. Okay, so I've kind of taken one of the steps outside of n-integrate, done it manually, once and for all at the outset, and in doing that, you'll see that the computation time for doing this plot is reduced because n-integrate doesn't have to do this work anymore. I've actually done it manually for it. Okay, it's just showing you one of the steps that's carried on inside n-integrate. So here's another example that's a highly oscillatory integral. It's a notoriously difficult problem. If I give it to an integrate, it immediately comes back with this answer. And moreover, if I give it even a higher working precision and ask for an even more accurate solution, it comes back straight with this answer. But this is a notoriously difficult problem, so how was it able to do that? And the answer is we can get some insight into what's going on by looking at where in integrate is sampling this function and the actual values. So this is a little thing here using the evaluation monitor to collect the points at which an integrate is sampling the integral. And it's plotting these sample points, the distribution of these sample points, and how the function is varying at these sample points. Okay? So look very closely at this distribution. Now, if I make a black box function here, preventing n-integrate from going inside that, then what you'll see is I actually get a different situation. N-integrate will fail to converge, and it's kind of trying to step down the sampling points into the region where it thinks the oscillatory part is occurring, but it doesn't know exactly where to distribute these values in order to improve the solution. So what exactly did n-integrate do? What it did was use a different set of basis functions. So if we have the set of polynomials, they look like this. What n-integrate will do is it will look at creating custom oscillatory rules, quadrature rules, by analyzing the function that's involved in n-integrate. And it will try to make a corresponding linear differential equation. And then it will look at the basis functions that are involved in this linear differential equation. And it will try to use those basis functions as a basis for its quadrature rule. So again, this is an example. This might be a naive way to try to sample the This might be a naive way to try and sample this oscillatory integral here. Here I have a discontinuous part, is the ceiling function, a Bessel function, and then some argument of the Bessel function. So what nintegrate does is it splits it into three parts. First of all, it recognizes that the ceiling function is present. So it knows it has discontinuities, and it knows where those discontinuities are. They occur at every integer value. So it knows it has to split up this region into three different parts. Then it will try to find a quadrature rule that corresponds to Bessel, the Bessel function that it sees, and it will find this linear differential equation. And then it will look at the argument of the Bessel function and see how this equation varies in these particular intervals. And it will see this is a very rapidly oscillating solution, and this is not so rapidly. And it will use a different set of quadrature rules and a different set of basis functions for each of these pieces. So another example is if we want to find a linear solution of a system of equations in high precision. Okay? But I'm not necessarily interested in hundreds or thousands of digits. I'm interested in a range, for example, that's typical in optimization or in ND-solve, which is only like quadruple precision, 32 or 64 digits of precision. What can I do to try and speed up solving these linear systems of equations? So one way to do it is use a procedure called iterative refinement. I'll solve the system in machine precision, where it's extremely fast to do, and then I'll refine it and build it up piece by piece, rather than trying to solve it all in one go in very high precision. So here's a basic idea of that. Each time I solve a system of equations in machine precision, I build up a number of digits of a solution. Block by block, each solution in machine precision gives me more and more and more and more digits of my arbitrary precision solution. Now, in order to do that, I need certain estimates of the system. I need certain properties of the system. I need to know about the precision. I need to know the dimension of the system. I also need an idea about the conditioning of the linear system, okay, because that's going to affect how many good digits I get each time I try and refine my solution. So this is a little plot that shows how much faster is it to build up this solution iteratively compared to just solving it directly in a high precision way. Okay, and this is a panorama of that picture, and this is the crossover here. Okay, so you see at low precision, this iterative refinement method is almost always faster, and over here it's like 30 times faster. Okay. So the larger the dimension of the system gets, for low to moderate precision, the faster and faster this iterative way of building up the solution works. But if I want a really, really high precision system, then I'm still better off using the direct method up here. But if the conditioning of the system gets worse, then this picture changes. And the direct way of solving the system gets better and better. And then suddenly, if the conditioning of the system is so bad that I can't even use machine precision, the conditioning is 10 to the 16, then I get no more good digits each time I try and refine this system using machine precision. And there's no point using the iterative refinement method.
What is the scale of the condition for the value?
Here I've plotted the precision against the dimension, and this is the logarithm of the condition number. So it goes from 0 to 16, which is the full machine precision. Yeah, it goes from nothing, which is the best possible scenario, which is almost never. And so here's just a couple of examples here. This is the timing now of the iterative refined method and of the direct method. And in green, I've plotted the method that's chosen automatically by Mathematica. And this is actually the runtime, so it includes the estimate itself for the automatic method to be selected. And what you'll see is it does a very good job of following the optimal method here, the iterative refinement method, up until the point where the direct method gets better, and then it goes off and uses the direct method. And these are four different scenarios, depending on real, complex arithmetic, whether the condition number is slightly worse, or whether we're actually solving for multiple right-hand sides. And in all of these scenarios, you see the automatic method picks up the right characteristics of the system. So the second half here of the talk, I'm going to talk about differential equations. That's mainly because the dynamics that occur in differential equations are so varied that this is where a lot of technology has gone into Mathematica in order to try and resolve these different types of dynamics. There might be ordinary differential equations, boundary value problems, delay differential equations. Now we have differential algebraic equations, partial differential equations. New in Mathematica 9 is parametric differential equations, and I'll also show a brief example at the end of events and discontinuity detection. Now, an interesting thing about the differential equation is that it's not like solving a linear system. We can't just get a condition number estimate at the beginning of solving that linear system that tells us how that system behaves, because the character of a differential equation might change during the evolution of that system. So locally, it might have certain properties in one region that aren't present in another region. And so we need strategies and methods that can locally adapt themselves. So these are just a couple of very quick examples about ND-solve. Here it's just a system of differential equations. What I'm just showing you here is that when ND-solve tries to put these differential equations into a canonical form, it's going to need to have this y primed on the left-hand side, and it's going to need to solve a system in terms of y primed. But y primed also occurs here. So when it's unraveling this system, trying to get a linear system for y primed, it notices this, and so it will generate two branches or two particular solutions. In this example, this is the interpolated solution, and these are actually the grid points found by the numerical solver, which is done step by step, according to some kind of local accuracy criterion. So in a boundary value problem, I have not just a starting point, but I also have a starting and an end point which bound the motion. In a delay differential equation, I have a history. Here, I have a delay or something backwards in time, and I need to give an initial history function. And what you'll see is you'll get these breaking points. This solution is piecewise continuous, and then there is certain breaking points here that build up in the history of the delay differential equation. Then there's a partial differential equation which has a dependency on more than one variable, and then you have partial derivatives in terms of more than one variable. So the first thing I want to show you is using this kind of monitoring of Mathematica to get the data out of ND-solve. I've written a little order monitor function that will just go and say to the method, what size order are you at every single time step? And then if I solve this system using my little order monitor function that sows and reaps data at every time step, I can then plot at every time step what the order of the integration method was. And you see that it adapts itself locally in order to satisfy the local error tolerances as the system evolves. So that's one thing. The methods locally need to be, for optimal efficiency, need to raise and lower the order of accuracy. A second thing that they need to do, the methods, is to be able to detect what's called stiffness. So I'll give you an example of that now. This is the van der Pol system here that I'm going to use in a number of examples. And I'm going to set up a little function that will monitor whether the method that I'm using is stiff or non-stiff. It's going to ask the method, are you a stiff method or are you not a stiff method? So here I'm going to get a problem, the van der Pol problem, and I'm going to try and solve it with a method that's not appropriate for a stiff system. And ND-solve will say, oh, this system appears to be stiff, because this actual method, although it's not appropriate for stiff systems, it has a little monitoring device in it that says when the system looks like it's becoming stiff. And it will suggest another method to go and use to solve that system. So if I actually do use that method, the stiffness switching method, I'll show you how that behaves for this system. Okay. So these are the two solutions of the van der Pol system. And the stiffness is not these sharp peaks. Okay. When you have these very sharp peaks, the ODE solver has to choose a very small step size. Okay. And when it chooses a very small step size, it's resolving fine detail. And an explicit method is fine for that because it's using a very small step size. The regions of stiffness are just after this when it comes back up again, and there's this change around here. Okay, so these are the regions. So every time there are these sharp peaks here, it's fine just to use an explicit method because the explicit method will be using a very small time step, and it's going to be resolving just fine this small detail. It's when the explicit method tries to start using a large step, but there's a change in character in the differential system. That's when it gets into trouble. So what NDSolve does is here I've plotted the time steps that have been taken by NDSolve, and the blue ones are the explicit method. Okay, when it's had to check this rapid variation according to control the local error, it's been working just fine with the explicit method, the blue method. But when the blue method, after resolving this fine structure, it's come back up here, then it's gone into trouble and it's switched over to using a stiff method. That's this red method here. Until it's got to the next part here and it's able to go back again to use an explicit method. Then it goes back to a stiff method, a non-stiff method, a stiff method. And you see it switches backwards and forwards according to the local behavior of the differential equation. So one of the new features of Mathematica 9 is sensitivity analysis. Here I'm going again to look at the van der Pol equation, but this time with a parameter inside it. This is a very nice feature if you're modeling something and you have a parameter available for modeling that, and you want to try and choose that parameter to solve some property. So when NDSolve, or parametric NDSolve in this case, sees a system of equations and it sees a parameter inside, what it will do is it will add an additional set of equations called sensitivity equations that will allow the characteristics or the changes in that parameter to be modeled. So here's an example. Here I've given it in the form of a second-order differential equation. NDSolve is going to split it into two first-order differential equations. And it's going to add these two sensitivity equations that are essentially going to allow me to study the behavior in terms of this parameter mu. What this parametric NDSolve does is it returns something called a parametric function. It's no longer an interpolating function, it's a parametric function, which has additional information inside it. And when I give it a specific value of a parameter into the parametric function, then out pops the standard interpolating function that's part of NDSolve. Okay. This is for a specific set of specific value of this parameter that's fixing the differential system. It's no longer a family of solutions, it's a specific value. So let's just look a little at the solutions here. So this is the solution at the end point in terms of this parameter. If I vary this parameter around 2.34, this tells me how the solution at the very end of the interval has changed, and it looks like that, which is okay if all I'm interested in is the very end of the simulation. But what if I want to know, like I'm not happy with this behavior, I want to know, well, where did this majority of this variation come from? Okay? Then I really need to know about how did nearby solutions diverge during the integration? Okay? And what I can do now with this parametric NDSolve is I can also find the derivatives of the solution in terms of the parameter. And I can plot my solution, but I can also plot locally the derivative or the sensitivity in terms of that parameter. So that's what's happening here. I've got one particular trajectory for the value 2.34 of mu, but locally around it, I've added the derivative in a positive and negative direction at that parameter value to see in certain regions it's very insensitive to the parameter, but in certain regions it's very sensitive to the parameter. So depending on where I'm modeling that parameter, I can decide whether I'm happy with that behavior or not. So I have two more examples. One is differential algebraic equations. So in order to solve differential algebraic equations, there are a number of ad hoc numerical methods that do that. But the most robust and reliable methods require that the problem be specified in a certain form for a numerical solver, and that's a so-called index 1 form. And that has this kind of structure here. The y's are the algebraic variables now. And if the Jacobian of this algebraic constraint here is non-singular for all time, okay, then this is an index 1 problem. However, if this Jacobian becomes singular, then it's no longer an index 1 problem, and my numerical solver won't be able to use the form that's been specified. So what does ND-solve do? Because you might just pick up a textbook and you might say, well, I just got this differential algebraic equation. I don't know if it's index 1 or index 2 or whatever. What is the differential index? So Mathematica will try and do this analysis for you. It will say, well, does it look like it's an index 1 problem? If it doesn't, then it's going to try and use a number of index reduction tools to try and transform that problem. Okay? Then it's going to post-process them. It's going to try and find some consistent initial conditions to get that differential algebraic system started. And then it's going to use a variety of actual integration methods to try and carry out that integration, depending on what the form of the result that came out of the system was. So that's kind of a flow chart of how ND-solve solves differential algebraic equations. Here's a very simple one. So here's the differential part, and here's the algebraic part. And y is my algebraic variable. I just give this to ND-solve, and it solves, and I can just plot the solution. This was actually an index 1 DAE. But what if I give it something else? So here's an example. This particular DAE is index 2. Okay, it's a very, very simple example. This is my differential equation, and this is my algebraic equation. But my algebraic equation involves the differential variable. It doesn't involve x2, which is my algebraic variable. Okay, so this is not an index 1 problem, because the derivative of this with respect to x2 is 0. It violates that Jacobian condition. So what do? I differentiate this second equation here and get a differential equation here. And then I use that first one to resolve as my algebraic equation. So in a sense, I've differentiated one time the original system, and I've reduced that now. This is now an index 1 problem. So this is the kind of transformation that you'd have to do by hand to reduce your system. But ND-solve would just do this for you. So if I give the original system to ND-solve, it says, oh dear, I tried to solve this system, and it's supposed to be an index 1 DAE, but you've actually given me an index 2 DAE. So it will give you information about what that system is too. So I say, well, okay, why don't you just use this method and try and reduce the index yourself of this system? Go away and try and reduce the index of the system. Put it in a form that you think is appropriate, and ND-solve just does that and is able to give you the solution of this differential algebraic equation. So my last example is of discontinuous equation, a switching function. What happens is, normally when you solve a system of differential equations, they have to have some assumptions about smoothness, Lipschitz continuity, in order to have a unique solution. In this particular example, I've said, well, when you hit a certain region, instead of using this function for the right-hand side of the differential system, start to use this function. So I might be modeling, say, air conditioning, since we're moving towards the summer. When you hit a certain temperature or go to a certain temperature, switch the unit off. When you go back up to another certain temperature, start switching it on again. And so I'll be switching between these two different types of behaviors of the system. One might be dissipation of energy, one might be, the air conditioning unit working. And then I'm going to do the same trick again. I'm going to hide this actual switching function from ND-solve. I'm going to prevent ND-solve from doing anything, going inside it, and it's just going to treat it like a black box function. Let's see how ND-solve does with that. So away it goes, turns away, 85 steps it takes, along it goes, and then it gets into this region where the function starts, we start switching the right-hand side, okay, and the numerical solver starts to get into a little bit of a problem here, but then it carries on, and it seems like everything's fine. So it did actually find a solution. If we look at the actual step sizes taken by ND-solve, then we see at the beginning it was fine, but then it got into this chattering state here. It tried to really shut down the step size here to try and get something that looked accurate enough in order to jump over this discontinuity. It kind of chugged away, and then it got back up again. And it's around this region where the solver got into difficulty. And the problem is, as it shuts down the step size, it might continue to use the wrong right-hand side in the solution of the discontinuous system. So what does ND-solve do? Well, it will use something called an event, a differential event. It will try to determine when the characteristic of that system seems like it's changing. It will see that if function, and it will add something called an event. So we have this event modeling language now in ND-solve using when event. And it will put that in, and that will be monitored as the differential equation evolves. Okay? And then when something looks like it's changing in character, then it will try to localize that character, and it will decide what to do. And automatically, it will decide to jump over discontinuity, try to find very accurately that discontinuity, and tread carefully over it. So now if I give this symbolic form for the function, ND-solve is now able to solve it in 14 steps instead of the 86 steps that happened before. And you see here, almost no difficulty whatsoever here, finding this discontinuity and treading over it. It actually localized the discontinuity and then restarted on the other side with a different right-hand side. So maybe that makes a difference to the computation time, but does it make a difference to the quality of the solution? Well, what we can do is to try and accurately detect where exactly this discontinuity is using high precision. So this is the solution found by ND-solve, just naively letting it use a black box function. Okay? And what you'll see is when it got into that difficulty with the chattering of the step size, when it actually integrated across the discontinuity, it introduced an error of almost 3 orders of magnitude into the solution. And if I'm modeling a parameter or something like that, it's introducing this error throughout the whole interval here, which is apart from the efficiency aspects of it shutting down the step size and getting into difficulty, it's actually introduced a huge amount of modeling error here. Whereas ND-solve, by analyzing that and by treading carefully around the discontinuity, was able to locate the discontinuity and then carry on the integration, giving a much smoother kind of error distribution. So it's a whirlwind tour. I hope it wasn't too fast. And it's just a sample of the methods that are automatically chosen by Mathematica with a focus on the numerical computation. So one of the goals is to make the methods to be easy to use, even despite the fact that the implementation can be quite complicated. I hope you've seen the use of these monitor options to get some insight into how the methods are behaving, how to inhibit these, the default kind of processing that goes on in Mathematica to get some idea of what kinds of modifications it's making. You've seen some examples of how being able to symbolically compute the derivative is important for efficiency and accuracy. The ability to symbolically analyze and transform a problem can give benefits. The ability to compare the cost of 2 methods at runtime and select between them. And also how local characteristics can affect the selection of a method. It might not be, a method might be good in one region but not in another region, how we need to adaptively swap between the two. So it's obviously something that we're still learning. With new functionality that goes into Mathematica, we learn new ways of using the system to try and improve it, and I hope that's at least given you a panorama of the situation. Thank you.